Okay, hello everyone and welcome back to my video. This week I will be presenting on phase shift keying. It is a part of my presentation for the subject of EEE 3522, which is Communications Engineering. Hi, my name is Nabil and my metric number is 209273. I will present to you on phase shift keying, and I hope this video can help you understand digital carrier modulation and its importance in communications. So, people have been asking, what is digital communication? So, in digital pulse modulation, the digital signal to be sent is converted into analog signal and sent over copper wires. At reception, the received signal is converted into original digital signal. Let's say, if the digital signal is to be sent through space, some modulation technique is to be adopted. In this context, phase shift modulation are one of the method used. Um, Later on, I will be explaining in detail what is phase shift modulation. So, PSK in communication. Digital signals such as telegraphy and teleprinter signals are often required to be transmitted over long distance by means of radio wave. Therefore, some type of modulation is to be used. It could either be in ASK, FSK, or in PSK format. ASK is an acronym that stands for amplitude shift keying. FSK is for frequency shift keying, and PSK is for phase shift keying. In a binary phase shift keying system, or BPSK for short, the sinusoidal carrier wave of a fixed frequency, we can denote them as FC, and a fixed amplitude, we can call them AC, is used to represent binary symbols 0 and 1. Specifically, for BPSK, the symbol is 1 bit. The phase of carrier for one symbol will be a shift of the signal phase angle by 180 degrees. So here is an example of how the digital signal can change the modulated signal relative to the carrier wave. Now, take a look at my cursor carefully. This is the digital signal. It can be in a random pattern as long as it is between 0 and 1. So here is a high frequency carrier signal. So as you can see here, when the digital signal changes from 1 to 0, there is a phase shift of 180 degree of the carrier signal. So this change usually happens during the modulation. Meanwhile, at the demodulation side, this phase shift will, how do I say this? Will shift back to its original signal. So I have made a simulation on MATLAB to prove that this can be happening. This is a simple structure of a demodulation, pardon me, this is a structure of a modulation PSK circuit. It is a bit hard to explain, but for your understanding, it starts by having two initial signals. So here is the digital signal. We can call it Bernoulli binary. And here is the sine wave for the carrier signal. So it will go through this first scope. The outputs I will show on later on. And it will have to go through some form of gain and multiplication between the two. And this is the output. Now let's look into the output. Okay, firstly, this is the initial random Bernoulli binary that we have included in the circuit in the previous slide. So it starts from 0 and then 1. And then looking back, it has to go through some form of gain, and there's a subtractor for this. So what this does is that it actually converts the 0 and 1 signal into a polar high and low signal, meaning it is between -1 and 1. So this is the graph. So we can see that the phase shift is done during the change of the digital signal from low to high, which can be represented in this graph here. And then we can continue on with the simulation of a full complete circuit of BPSK modulator and demodulator. And this is how it should look like when you run your simulation. Bear in mind, if you look forward into simulating this circuit on your own, you have to install signal processing toolbox as well as communications toolbox. So you can run this on MATLAB through Simulink. So here are the output of the previous circuit. So on the most bottom graph here, this will be your input of the digital signal. And for the carrier wave, it can be at any frequency it can be at any frequency as long as it is very high in order to fulfill its carrier properties. You give me a few seconds. Okay. So this is the digital signal, as I said before. Focus on this third graph here. This is where the modulator shifts the carrier wave phase shift. For this graph specifically, it is in the unit of radian instead of in degree, meaning instead of we compare it from 0 to 360, we just compare it in units of radian. So for example, here we can see it is from 0 to 1. Then the signal should be the exact opposite of the digital signal. So it becomes 1 to 0. Is for the second graph, this is the AWGN channel. It stands for add white Gaussian noise. I will explain this deeper later on. And for the uppermost graph, this represents the demodulator part of the BPSK circuit. Since this is a demodulator circuit, you have to make sure that the random integer generator signal here and the demodulator has to be similar for you to verify that the whole BPSK circuit works exactly as intended. So let's compare the first graph and the last graph. We can see that the shape of both graphs are exactly the same, which means that the simulation was run perfectly. So now begs the question, what is AWGN? So add white Gaussian noise is important in simulation. It is commonly used as a model for channel noise in many communication simulations. It is a type of random noise that has a flat frequency spectrum and follows a Gaussian probability function. By introducing noise, they can analyze the system's ability to recover the transmitted information in the presence of impairment caused by noise and other factors. So what this means basically is that it makes your simulation practical instead of it running in ideal situations. So apart from BPSK, there is also QPSK, which is quadrature phase shift keying. For BPSK, the symbol is one size bit, but for QPSK, the symbol is 2 bits. The binary data is first converted into 2-bit symbols, which are then used to phase modulate the carrier. Pardon for the typo here, this should be 2 to the power of 2 is equals to 4 combinations, because since one symbol can be in 2-bit, it can either be 0, 0, 0, 1, 1, 0, and 1, 1. Now, let's look into how the phase can change depending on the bit. Oh, okay. I guess that's all from me. Thank you for listening. I will be explaining on other topics in the future. Bye bye.